Okay, we are now doing question number 7. In part A, we are asked to find the forces acting on the keystone. So in effect, we are asked to draw a free body diagram for the keystone. Right, so the forces acting on the keystone would be the force L exerted by the load placed on top of the keystone, the weight W of the keystone. We are told that the two stones in contact with the keystone exert forces on the keystone that are perpendicular to the sides of the keystone. Therefore, we draw these forces P at 90 degrees to the side of the keystone, and by simple trigonometry you can see that this force P makes an angle of 10 degrees with the horizontal. Similarly, there's another force exerted by the right hand side stone on the keystone, and this is also perpendicular to the side and therefore also at an angle of 10 degrees to the horizontal. Right, part B, we are asked to find P using a scale diagram. Scale diagrams will not give answers which are as accurate as those obtained by calculation. So personally I would not recommend it, but this is how it's done. Right, we know that the four forces, when they act on the keystone remains in equilibrium. This means that the resultant of the four forces must be 0. So if you were to draw a vector diagram showing the summation of these four forces, you end up with a 0 vector. In other words, the vectors will all come back to the starting point, right? So you form a closed polygon. Right, so let's start. The scale chosen is 1 centimeter representing 1000 newtons. Hence the force of 4600 newtons will be represented by a vertical line of vertical vector of length 4.6 centimeters. Right. Similarly, the force W, the weight, which is 600 newtons, will be represented by a vector of length 0.6 centimeters. Right. We do not know the length of P and Q, that's what we are trying to find, but we do know their directions. They are directed at 10 degrees to the horizontal, so we use a set square or a protractor to draw a line that is perpendicular, a horizontal line, right? Then we use a protractor to draw a line that is at 10 degrees to the horizontal, and thereby giving the direction of P. Alright, so we draw a guideline. We do not know the full length of P. For Q, we do the same thing. We use a set square or protractor to draw a horizontal line, and we use a protractor to draw another line that is in the direction of Q, namely 10 degrees to the horizontal. Right, so we have managed to find a point of intersection here, right? So so this naturally gives us the lengths of vectors P and Q. So now we can safely draw vector P as follows and Q as follows. Right, we have completed our scale vector diagram, and we simply use a ruler to measure the lengths of P and Q. Right, since the diagram is obviously symmetrical, P and Q are equal in length. Right, so if we use a ruler and measure P, we'll get 15 centimeters. So this tells us that P has a magnitude of 15,000 newtons. Same with Q. Q is also 15,000 newtons. So that's the answer to part B. P and Q are both 15,000 newtons in magnitude. Okay, in part C, we are asked to repeat the calculation, but now by using pure theory. Right. So we make use of the same scale diagram, the same vector diagram in part B. Okay, we notice that this angle indicated here is 10 degrees, right, by simple trigonometry. Same with this angle, 10 degrees. Okay, so if we simply extend this horizontal line here, right, we will find that it is actually perpendicular to the vertical side here, right? So I draw a right angle here. Okay, so we are trying to find P, right, and Q, right? So so we can see a right angle triangle here, right, with P being the hypotenuse, and so we can easily say that same for Q, there's a right angle triangle here, right? So we can easily find the length of this side by using trigonometry, simple trigonometry, and similarly we can find the length of this side. So right, so for example, for this right angle triangle, the length of this side in terms of P will be P sine 10 degrees, and similarly for this right angle triangle, the length of this side will be Q sine 10 degrees, and obviously P and Q are the same. Okay, now we can calculate. We know that the full length of this side is 4600 plus 6200. Okay, so L plus W will be P sine 10 plus Q sine 10. Sorry. Yeah. Okay, therefore we can easily calculate P, right? Because P and Q are equal by symmetry. Okay, so if we simplify this first equation, we get this second equation. Okay, so P is now easily found to be 15,000 newtons in agreement with our scale diagram. Right, there is actually a more direct way of solving of calculations, of doing this calculation. Right, so let's show that alternate method. We look at the original diagram, the original force diagram. Okay, we notice that the keystone is in equilibrium, therefore the resultant vertical force must be 0. L and W are both purely vertical forces, and you notice that P and Q both have vertical components. They are slanted upwards, right? Therefore we can easily find the resultant of P and Q, right? So P sine 10 is the vertical component of P, Q sine 10 is the vertical component of Q, and if you add these two vertical components, they must balance the other two vertical forces. So we get back the same equation as we did for the earlier calculation. Okay, so that again gives us the same answer for P and Q, 15,000 meters. Okay, that's it.